we are going to focus on, this should say day 3. We're going to focus on artificial intelligence and biostatistics. And our speakers today will be Patrick Bangert, Peter Kim, Sushant Singh, PhD, and Juhua Song. So let me introduce our first speaker. Patrick Bangert is the VP of AI at Samson SDS. So without further delay, let me stop sharing so that we can begin to hear his talk. Thank you for being here, Patrick.
Yeah,
Please
thank you for
continue.
having me.
Okay.
Good morning, Amy. Good morning, everyone. Glad to be here. So I'm going to talk to you about the AI pipeline or the data science workflow, depending on what vocabulary you want to use for this. And since this is a conference about careers, I'll try to, as I go through this, at each step, mention something about the career progression. Since this is a small and cozy group of people, please do feel free to stop me at any point in the presentation and ask any questions that you might have. I lead the AI department at Samsung SDS, which is the IT company in the Samsung group. So you might know Samsung better for making things like mobile phones and television sets. And we do have a software arm that runs the data centers, writes the software for all these nice devices, and does the AI modeling. And that's what my department does. So if you talk to your phone with a natural language processing algorithm, you look at it and expect it to open up by recognizing your face or your fingerprint or something. All these are AI models that interact with you. Let's look at this workflow or pipeline. This is, of course, all my opinion. There are 5 technical steps in the pipeline, and they are bordered on the left and the right-hand side by 2 steps of communication. So there's 7 steps in total. At the beginning, this communication step right here on the left-hand side basically is asking, what exactly is the task that we're trying to solve with data science or AI? What data do we have? What data might we need to collect? What kind of domain knowledge do we need to collect? Who do we need to be on the team? What's our timeline? What's our budget? What's the expected ROI? So this is a fairly complex step at which actually most of the mistakes are made. Then we progress through the step of actually obtaining the data and cleaning it up. Cleaning it up usually involves removing data, the data that is somehow flawed. And then we label the data, which is usually the point where human domain knowledge is in some way put into the data set. This is most obvious in the case of images, where a human expert might have to shade in the areas that are relevant. So for example, if you're looking at an MRI scan of somebody's brain, they would need to then, sorry, what happened here? They would need to shade in the area of the brain tumor or something like that. On a picture of a road scene, you might want to put a bounding box around cars and people. That kind of human knowledge is injected. Next, we develop features. By features, I mean those parts of the data set. If it's a tabular data set, that would be columns. If it's an image data set, parts of the image that are particularly informative about whatever task that you're trying to do. Then you have to choose which kind of model you're going to use. Is it going to be a neural network, a decision tree, a support vector machine, whatever? That's model selection. The algorithm that creates that model needs parameters to be specified, and these parameters need to be tuned to the data set that you have. And so that's called hyperparameter tuning. That's a significant step of work. After all that's been decided on, you can perform the actual AI training, get your model, assess how good it is, and then deploy it, which is usually called inference. So inference is where you have a finished model that's been deemed to be good, and that's now put into whatever practical task it is in place and is operational, giving you the results that you need. Finally, there's a change management step, my personal pet peeve, because most projects fail at this point, because here you need to convince real users to actually do what you expect them to do. You need them to change their way of life in some fashion and adopt this new technology you've created for them. And the standard answer, as you all know, to change is no thanks. So it's at this point that the problems happen. So to sum up, the difficulties, the frustration happens at the very beginning, where you need to nail everybody down on a common definition of whatever the task is and what resources you have available to solve it. That is usually a significant challenge. 80% of the risk of failure happens at the very end of this process in the change management step, where, as I say, users often say no thank you to a fully developed product, and that this can of course put the entire effort in jeopardy. So from a point of view of data science careers, at this point, I want to point out that the major influence on the success or failure of your career, or the major qualifications as a data scientist to enter the career path, are actually completely unrelated to mathematics or statistics or anything like that. The prime qualification is one of interhuman communication, and communication in three major areas, right? There's verbal communication, as we're talking to each other. There is written communication in terms of prose, where you write essays or emails or something like that. But probably one of the most important ways of communication is PowerPoint presentations. And it's different from prose and verbal. It's a skill to its own. And this is the language that you communicate with senior leadership with. And this is how you ask for resources, how you ask for budget, how you communicate the timeline. And as I said, most of the frustration and most of the risk are not related to technology or mathematics or statistics or science. They're related to communication. So if you remember one thing from this talk, it's that the major onus on data scientists is not scientific, but it is communication. So I can only urge you to focus on that.
Mr. Bangert?
Yep.
I had a question for you. In the stage of like the data labeling that you were talking about, where you put parameters around what the artificial intelligence is supposed to be looking at, is that how most of like Samsung's algorithms generally work, where you guys are setting those parameters rather than letting the software actually pick its own parameters per se, in order to gauge patterns, for example?
Good question. So some data sets do not need to be labeled. So for example, time series data sets kind of label themselves, if you will, because for time series data, you're trying to forecast what happens in the future. And so all you do is you wait for the future to be the past, and there's your label. So that's objective. But some data, for example, images, like I said, do require the injection of human knowledge by saying this part of the image is the brain tumor or the car or the obstacle on the road that you need to watch out for. So that needs to be put in. Now you ask for parameters. Parameters is really a part of this fourth step here, where we're talking about hyperparameter tuning. That is a necessity. It's not a necessity because Samsung says so. It's a mathematical necessity. So everyone does this. Yes, you do need to select the parameters of your model, quote unquote, correctly. If you choose a poor value of those parameters, your model will not be very accurate. And the influence on model accuracy is very significant. So you have to choose the right parameters. I'll go into in maybe 10 minutes or so how you actually do that. You don't do that by person. You do that computationally too.
Okay.
So hyperparameter tuning is not a manual activity.
Okay. Thank you, Mr. Bangert.
So continuing along that thread of where the work happens, this data part, the data acquisition and labeling part, consumes most of the work in terms of person work, right? So if you're thinking human resources, budget, then this is where it gets spent. And the other three parts are responsible mostly for the time delay, but not so much anymore for the human resources, right? So by the time you have a labeled and clean data set, you've spent most of the human effort budget that you have in the project, and the rest is now mostly computer. So all the work here is mostly done by the computer, not by people anymore, but it takes a long time. So that's the other thing to wrap your head around, is that usually when we interact with our laptops or desktops, we expect results to have to be put back, more or less instantaneously. With artificial intelligence or data science, that is not at all the case. When you're dealing with a realistic size data set and you want to train a neural network on it, let's say, and you want to choose the correct hyperparameters, that might be a computational task that might take 2 months, 3 months. Not of your time, but simply be between the time when you press the button and the result gets displayed 2 months later. So it's something to keep in the back of your mind that these steps do, on occasion, for realistic data set sizes, take a really macroscopic amount of time. So having said that, sort of on a 50,000 foot view, how do we do some of these things? So data labeling is the first part that I want to address here, and I want to talk about a technology called active learning, which helps. So here's an example for data labeling, right? So we've got this picture of these sheep over here, and we might want to identify where are sheep at all, or where are each of the individual sheep on the picture by drawing what's called a bounding box, so a rectangle. But you might also be interested in what is the outline of the sheep exactly. So this is more of a polygon boundary. Now, just to give you some background, we usually find that drawing these bounding boxes takes about 1 minute per picture by hand. Drawing segmentation boundaries like this, freeform, might take up to 5 minutes per picture. Now, a realistic data set size has several 100,000 images in it. And so you can imagine if you have several 100,000 images and it takes you 1 to 5 minutes per image to label it, you're talking about a multi-month effort for a team of 10 or 20 people to do that job, right? So that's what I mean by 80% of the work. I mean a lot of work. So this is actually a cottage industry. There are multiple companies that have 5 to 10,000 employees, full-time staff, who do nothing other than draw bounding boxes and shade in areas all day long for various data sets. So again, this is a very serious job that takes time. Now, the sheep is, of course, a silly example, but it's just kind of nice to look at. Where this becomes relevant is, for example, medicine. So COVID-19 obviously is preventing us from seeing each other in person. And here we have an example where we can actually diagnose whether or not you have COVID-19 based on an X-ray image of your lungs. So your lung should not be looking like this. Okay, this is a bad lung. You don't want to have this. This is a good lung. So if you take an X-ray image of your lungs and it looks like this, then the algorithm would say, okay, based on the shape and the where the mucus is down here, you've got a problem. You've got COVID. To make that happen, again, these images needed to be labeled, and of course they needed to be labeled by doctors. So now you have hundreds of thousands of images, several minutes per image. You get a third problem. Your staff has to be fully qualified physicians that are, of course, expensive and rare and should rather be treating patients. So again, data labeling is a very serious issue in artificial intelligence. So there is this idea of information gain in all of data science, basically. It says, how much information does each data point provide to the model? And it's not the same, of course. Some data points supply more information than others. Consider, for example, if you have two data points that are similar to each other. The first one that you label or that you input into the workflow, that provides a certain amount of information. The second one doesn't. And so you think, okay, I should be sorting my data points in order of this information gain, so that out of the groups of similarity, I take one example and promote it to the front of the queue, and the other examples that are similar to it need to be pushed down to the bottom of the queue, so that I label the most informative data points first. Now, of course, that's a clever idea, but we don't know how to do that. The order is unknown to us. So we have to gradually find out. And that's the idea of active learning. It's a general principle of artificial intelligence, and you'll find a lot of literature if you're interested in it. What basically happens is you label a little bit of the data and give it back. The computer then sorts images according to what it thinks should be done, gives you back the most informative ones, you label them and give it back again. It learns what it can, resorts again, gives it back to you. And you continue in this conversational style back and forth until at some point the computer is able to say, I've got such high confidence in my judgment that you can stop labeling the data at this point. And we find that it usually occurs somewhere around 10% of your data. So it's a huge labor saving device to make that happen. And you can see the experimental proof down here. As you label more and more data set going to the right-hand side of that diagram, the accuracy grows in a very haphazard fashion if we label the images in a random order. However, on the orange curve here, the accuracy grows both quickly and almost monotonically as we label the data set. And around, in this case, 16%, we have achieved the highest accuracy that we're going to achieve. The other 84% are basically irrelevant. They do not provide any further information to the problem. So here is one technique that you can use in artificial intelligence to reduce the amount of labor that you have to put into it and still get out the same accuracy at the end. So that's one of the techniques you can use early on in your data science career to get highly accurate models with less investment. And of course, investment again comes up at this communication step at the very beginning, when your management asks you, great, so how much is it going to cost me to do this data science project? And that communication step of it's either going to cost you $10 million or $1 million is absolutely crucial. And a technique like active learning can assist you in reducing that cost. So let's talk about feature generation. Feature generation is something by which we want to separate the data points into diverse categories in advance of learning, right? So that we can say, okay, here's a bunch of examples of dogs, and here's a bunch of examples of cats, and so on. And a feature of these things are that they have legs, and particularly they have 4 of them, right? Four legs each. 3-legged dogs and 3-legged cats are possible, but they're very rare. And so this is what I mean by feature. And features have to be selected. In other words, what is the most telling feature about a particular category? So having 4 legs is a particularly useful category feature for animals, but having 4 legs is not a feature that will distinguish dogs and cats, for example. So you need to maybe think of a hierarchy of features that you can tease out of your data set relative to what you want to do, and then effectively separate a chaotically ordered data set into a structurally ordered data set by these features. Now, many processes currently do this by hand, where it is the data scientist who does manually the definition of what are the features, which are the more important features, and how are they going to be calculated. So you might easily spend a month or 2 of your time on feature generation, creating new features, as well as selecting among the features that are available to you, which are the most representative for the data set that you have. Now, what I want to point out is that it is possible to both generate new synthetic features as well as select among the available features the best ones automatically. It's not necessary any longer to do that by hand. Again, that saves you a lot of human effort time by exchanging it for computer effort. And this is an example of what is called AutoML. So AutoML, short for automatic machine learning, which again is a technique that you see in many places on the internet. So AutoML is a keyword to search for, and it will help you in doing some of this work. Let's go on to model selection and this hyperparameter tuning step that I talked about beforehand. Model selection is basically the question of which kind of model, and there are many choices, should I choose for this particular task that I have. And the philosophical answer to that is we don't know until you try, and that is the problem. It is one of the absolute holy grail questions of artificial intelligence of, can we tell you a priori which model will do the best job for a particular task? And at the moment, no, we cannot. We just don't know. It's a trial and error task. You have to expose your data set to various kinds of models and see who does best. And again, that's of course a process that can be automated, and that is another segment of the AutoML collection of techniques that I was mentioning earlier. Once you've chosen, the next question is, which hyperparameters? Now, I won't go into detail about this. I don't know where each of you is at in your journey to learning about data science and artificial intelligence, but there are parameters of the algorithm that make any of these models, which go by these names of learning rate and momentum and the size of the mini batch and so on and so forth. that are, sometimes they are just numbers, like the momentum and the size. These are just numbers. But sometimes they are more than that. The learning rate, for example, is not a single number. The learning rate is a number that gets adjusted as the training gets older and older. So actually the learning rate is a time series that you get to manually tune or automatically tune. And so again, here is a trade-off between doing some of this research yourself as a human, tuning these parameters to the task, or simply delegating that tuning task to a computer. And again, that is a part of the AutoML process. So now we've hit the three major aspects of AutoML, right? It's feature engineering, model selection, and hyperparameter tuning. These three things make up AutoML and allow you to create a model that is quite good by using much less human effort to make it. Now, one example of tuning that you might consider is to perform what's called a grid search, which is you say, I don't know what value this parameter ought to be having, but I know that there's a very small value and a very large value, and it's somewhere in between. So what I'm going to do is I'm going to break up this sequence here into many little buckets, and I'm going to try each bucket. I'm going to try this value, this value. And that's a grid search, because you need to do it for multiple parameters simultaneously. So you get not a line, but rather a multidimensional cube, if you will. So it looks something like this in 2 dimensions. And you will try at each point and come up with a result, and you will be able to do nothing more intelligent than basically pick the best one. This goes back to a technique called design of experiments that used to be popular a few decades ago. Design of experiment was very useful for designing physical experiments, for chemistry and physics in a laboratory environment. But for data science, we have access to a very different technique. And it is called adaptive search. Adaptive search starts with a grid search, a few of these points, as initializers, and then learns as it goes along, based on what it's already done, where it should be looking next. So this is something like you get dropped off in the middle of a mountain range that you've never been to before. It's foggy, and you're told to find the valley. Well, the only option you have, because it's foggy, you can't see very far, is to walk downhill. And eventually you get to the end of the downhill, the next slope starts ahead of you, and you kind of have to amble about until eventually, of course, you get to the bottom of the valley. Adaptive search works like this. You search a little bit in your neighborhood, you would develop a picture of what your neighborhood is like, and then you walk in the right direction and you try again in this new neighborhood, and you search and search until eventually you find. That can be made intelligible. It can be made very strategic, and adaptive search usually finds relatively economically the right answer. So again, this is the old style, the manual, human-dominated style of doing things, but there is a better, smarter, and automated way of doing this that will get you to the right answer. Now, what I've said is that you can automate a number of steps along the AI tool chain by basically delegating work to the computer and getting it to run trial and error experiments. Now, there's a cost, obviously, to doing this, which is that you need to do a lot more trial and error experiments than you would have done in the manual way. And that takes time. As I said before, each training step can take a macroscopic amount of time. It can take hours or even a couple of days, which means if you chain them up, it could take months upon months. And it does in real life. So how can we make that faster? And the answer to that is distributed training. Distributed in the sense of using more than one computer. So typically what you would need to do is you would need to collect a series of computers, and you would need to install various kinds of software utilities on them. They're named here, which will basically splice together that group of computers into a single large meta computer. And that will allow you to then program that computer in the appropriate fashion that it can act as a single whole. That's a lot of work in its own right. And you don't need to do it because there are tools out there in the world that have already done that for you. And so if you pick up one of those distributed training utilities, and again, distributed training is a key term that you can use in your Google search to find these tools. There are multiple available from multiple vendors to get this done. And what it then does is it runs those tasks that I was talking about on multiple computers, therefore cutting down the time it takes. Now, let's think back to grade school. We were usually asked by our teacher this question. If it takes one builder 100 hours to build a house, how many hours does it take 100 builders to build the same house? And the answer that the grade school teacher expects to hear is 1 day, right? Now, anybody who thinks about this question for a minute says, no way. 100 builders working on a single project, they're going to need management. They're going to have overhead. They're going to step on each other's toes. They're going to need to stay out of each other's way. So maybe the 100 builders will actually take even more time than a single builder because of all this chaos. And that's a good thought. In fact, if you try to use multiple computers for an ordinary task, there is often very significant overhead, and data suggests that the efficiency growth is logarithmic. It shoots up, but then it levels off very quickly at some point. And so we might be afraid that for artificial intelligence, the same is true. There's a very much diminishing law of returns for this. And it turns out that that is actually not correct. Very luckily speaking, artificial intelligence turns out to be an exception to this rule. And you can actually orchestrate multiple computers together to perform extremely well in concert. So here's an example. I could possibly give you many more examples, but this is just one example where we trained a natural language model. Distilbert is one of the more popular natural language models, something that you might find on your mobile phone when you give a command to your mobile phone, or you give a command to your Alexa device at home. Distilbert is the artificial intelligence technology that makes that available. You need a computer to train that model, and we looked at what happens if we use multiple ones. So the benchmark, if you will, is a single computer that has 8 graphical processing units in it. So it's a fairly sophisticated single computer, mind you. It's not the desktop that you would have at home. So already the single machine I'm referring to is a powerful one. But if we go from this one machine to 4 machines, we get a speed up of 3 times purely by the fact of using these 4 machines. Okay, so you say overhead is the one machine. Okay. If we go to 8 machines, we experience a speed up of 6 times. So in other words, the speed up holds steady at a linear scale by going from 1 to 4 to 8. But you pay an overhead price. However, because this is AI, you can use some special scheduling techniques to speed it up another factor of 2. In other words, by going now from 1 to 4 to 8, you're not speeding up from 1 to 3 to 6, but you're speeding up from 1 to 6 to 12. In other words, you get a super linear scaling as you grow with the machines. And the reason for that, quite simply speaking, after you do some analysis, turns out to be the RAM memory, the random access memory that each one of the GPUs provides. And that has an effect on your hyperparameters, namely on the batch size. The larger your batch size, the faster you can train. And with a certain batch size, you can also get good accuracy. Ultimately, the message is this: AI training is an exception to cluster computing in the sense that it will actually speed up your processing instead of costing you additional overhead. So using multiple computers is very, very interesting to automate all of the tasks that I was talking about beforehand. The punchline of everything I've said so far is that by automating AI, using AI itself reduces your human workload by about 50% upfront, and it significantly reduces the time delay in the back here by automating all of these tasks. Now, let me again find my way back to the career question, since this is a conference about data science careers. There are 2 aspects here. The first thing is, as a career data scientist or looking for a career in data science, you should be aware that these tools exist, because they will be good not only for you personally, because you will reduce your workload and your heartache and your headache, but you will be able to deliver a better project in less time and less budget for whoever employs you. So please be aware that these tools exist. Samsung, of course, is a provider of some of them, but there are plenty of other companies out there, so there is no vendor lock-in with any of these things. These are standardly available tools. The second conclusion in terms of a data science career is, again, this is the one message I want to leave you with, is put less emphasis on the technical, mathematical, statistical, numerical aspects of the data science work, and concentrate on communication. It is the aspects of communication, both at the beginning and the end, as I said in the beginning, that are actually responsible for all the failures out there. There's a popular statistic, and I'm afraid it's true, that 9 out of 10 AI and data science projects fail in the industry. 9 out of 10 projects fail. And they don't fail because the math didn't work out, or the model turned out to be bad quality, or somehow the data was missing, or the data quality was bad, or the technology didn't work out. No. Maybe 1 out of 10 projects fails because somehow the math didn't work out. 8 out of 10, 9 out of 10 projects fail because either the project that was engaged in was not the problem that the company had, so the communication step in the beginning turned out to be a total mismatch, or at the point of deployment of the product, of the final model itself, the users didn't use it. Those are the 2 risk factors here, and they occur a lot. You would be shocked how often this actually happens. So in the life of a data scientist, actually those are the important steps. And I want to show you a couple of images that make that kind of tangible. So I presume you've all heard of the parable of the blind people and the elephant, right? So imagine you have an elephant and you have several blind people. Obviously, they cannot see the elephant because they're blind, so they touch it. And depending on where you touch it, because the elephant is so big, you end up with a different opinion on what this thing is that you're touching. And that is very realistic for the kind of communication step at the beginning of an AI project. If you talk to several people who are immediately impacted by the problem, they have a different view of it from each other. You talk to middle management, they have a certain view. You talk to top management, they only care about the monetary aspect. You talk about the software developers, they talk about this technology and that technology, probably in terms of acronyms you've never heard of. Everybody brings a completely different point of view on what is hopefully a single task. And it is often the data scientist who has to disentangle that mess. And so this is unfortunately a quite realistic picture of what takes place at the very beginning of a project like this. Over the life cycle, it tends to look like this. As you begin to read the captions of each of these images, I would like to tell you that even though this is funny, and I hope you laugh when you look at this, it is unfortunately depressingly funny because this is an extremely accurate picture of what goes on in the real world out there. So let's have a look at a couple of these pictures. At the bottom right here, the tire on the tree branch to have a little kid swing about, that's what the customer really needed. But looking back at the beginning here, the customer was not able to explain it in that way. Yeah, he himself, the customer, him or herself, did not have a sufficiently clear idea that he was able to articulate. So what the customer said was this: a more sophisticated, somewhat less usable version of that. Now you can see in the communication, some communication mishaps took place. And so this is how the project leader understood what the customer said, right? This is what the customer said, and this what was understood. Again, you find that in human communication all the time, I'm sure, that person A says something and person B understands something completely different. And then the misunderstandings go further and further away from reality. Possibly the worst aspect here is that a consultant or the salesperson, if you will, describes it in glowing tones, and then the financial department invoices the customer in equally glowing tones. But the actual design process and the support process does not match up to that whatsoever, right? So these are the problems that the data scientist meets in real life as you go through a project. You have multiple misunderstandings by various of the stakeholders in your project. And you do very much have to cope with resource problems like budget and human resources and timeline. So I would encourage you to have a close look at pictures like the elephant picture and this one to get an idea of what you might need to do in a real data science project to get it across the finish line. In my world, data science is a team sport. There is often the expectation by customers that a data science project can be done by a data scientist. The emphasis being both on a data scientist as well as data scientist, right? The expectation is that a single person who is a data scientist will be able to just take care of it. And that is the most unrealistic expectation out there. I find that it typically takes a team of perhaps 10 or more people to do a single data science project. Now, it doesn't require all of these 10 people full time, by no means. But it requires their knowledge and expertise and input. And so three main groups that are involved is, of course, the management and the users, because they give the motivation for the project in the first place. And of course, the management provides the budget. You do need a domain expert, or typically speaking, multiple domain experts in whatever area you're dealing with, right? If you're dealing with medical imaging, you're going to need doctors. If you deal with automotive, you're going to need automotive engineers, and so on and so forth. And of course, you need the data scientists. And these work together in this kind of tree-like picture, right? If you cut the users out of your project falls over. It's missing its trunk, right? If you're missing the domain expert, it cannot hold the foliage. So you need to take into account that data science is necessarily an effort done by a team, and therefore you need all the usual team things like, project management and a team leader and all that kind of stuff. There's, of course, a risk and benefit analysis that needs to be done. I don't want to spend too much time on this. And it yields a business case that you need to defend. Obviously, the data science project needs to earn more money than it consumes. And that is a very crucial aspect of the data scientist's life, is to argue to management that, in fact, the process has a larger benefit than it does a cost. What I want to leave you with is this picture. This is not mine. This is the result of a very significant amount of psychology research that's been done over decades. And it gives you an idea of the mental evolution of a person who has been exposed to change. So when you go through a data science project, as I said before, the most significant step is when you're done with the science and you want to deploy that science to be exposed to real users. Then you meet this curve here, where people initially are afraid and ask, can I cope with this new situation? Whatever it is, right? It's new to me, and so it's a threat. And you go through all of these stages, and if you leave people to go through that process on their own, they will most likely end up in the points that you don't want. You don't want people to say what change and ignore you. You don't want people to just take off, and you certainly don't want active hostility. So you need to manage this process and get people through these stages so that they're reasonably happy at the end. And this process of managing that people go from can I cope being a genuine question to the answer being this is going to be okay, that's called change management. And change management in practice is something that falls maybe not squarely, but largely on the shoulders of the data scientist. So again, my encouragement to you is do along the lines of educating yourself about neural networks and training algorithms and hypothesis testing. Concern yourself with communication and change management, because they're the ones that will determine the success and failure of your project in a real scenario. So that's as far as I wanted to go, and we've got 10 minutes left for questions.
Thank you for that. Felt that talk was I have a question for you. You had a illustration that showed different members of the team when it comes to creating a product. And I just like to know, which member has the most influence? Is it the beta tester who comes back and gives you feedback on what they feel is not working, or Is it fine? Is it the finance department? Is the original client the person that makes the final decision in terms of who is it?
That is an excellent question, and the answer to that too, I'm afraid, is it's a team effort. Of course, there is some person who has the last word on any project, and that's usually the person who is responsible for the budget. So at some point in the product life cycle, the person with the budget is going to get antsy and say, you know, we're running out of money, we're running out of time, we're running out of human resources. Are you done finally? But and then it's up to you, up to the data scientist to come up with an intelligent response. But that's not the person who's usually most influential in the project. This is kind of the person who defines where the boundaries are that you have to obey. You have multiple people that are influential in the process. But if you're asking me who should be the most influential person in the process, I say it's the user. Unfortunately, in many projects, the user gets ignored until the product is done. My recommendation is to involve the user at the very beginning and involve the user throughout the project. This accomplishes some of these change management tasks as you go, because change doesn't hit them. They're actively participating in generating their own change. And that has a lot of benefits. It has psychological benefits to them, and it has scientific benefits to you. So if you're able to, I say, by design, make the most influential person the person who is expected to make use of the model you're making.
I see. Okay. Thank you. Thank you for that. Are there any questions? The floor is now open for questions.
I have a question. I'm a master's student in data analytics, and it sounded like when you're talking about automating the models, is that something that's not like standard practice? Because we're learning about that in school, but it kind of sounded like that's not something that's standard.
Well, it depends what you mean by standard, I suppose. Because if you do want to go through the full AutoML workflow that I outlined, as I say, it only is realistic if you do it with distributed training, because then you can do that in a realistic amount of time. If you do it on a regular computer, like a laptop or a regular desktop, AutoML will just take a very long time, and you don't have that time. In other words, it relies on an investment in computer hardware. And you will find that at universities, for the most part, you don't have access to enough hardware to make that happen. So is it standard? Well, once you get to being an employed data scientist at a larger commercial company, yes, it is, because then you will have access to the appropriate hardware. While you're still pursuing your master's degree, probably not, unfortunately, because your university won't be able to afford the necessary hardware. You need to actually carry it out. Or you'd need to do it on a toy problem, which then doesn't have practical consequences. But yes, once you're out there as a practitioner in the industry, yes, this is standard practice.
Okay, thank you.
I did have another question for you, Mr. Bangert.
Go for it.
Since I'm also a master's student in data analytics, so I'm kind of in the same boat as my fellow student who just asked you a question, in that there isn't a lot of exposure to auto machine learning through my degree path so far. Do you have any suggestions of where I could get some more like on hands interaction with that type of machine learning at this point?
Yeah. So if you if you Google AutoML, you will find a tremendous number of resources, and there are quite a few companies that make software to make AutoML a reality. You will find those as well. There are the likes of Data Robot and Data IQ, and many others, and of course my own company is in that list as well. And some of those you can get things like free trial programs available, things that you can download. Again, the challenge becomes having the hardware infrastructure to actually execute on those. But you can get some exposure definitely just by reading about it on the internet and trying to join one of these trial programs.
Okay. One other question would be is, since a lot of these programs are more geared towards infrastructure that is generally more powerful than, say, like a home desktop or a home PC, have you come across any that are more geared in kind of a smaller scale, say like for a home desktop or a small business or something like that, where resources are limited in that aspect?
Oh, these technologies will work for small resources. Absolutely. I mean, you can do AutoML on a single desktop, that has either no GPU or just one GPU. No problem. The software will work. It will just take a very long time. So if all you're looking for is exposure to the tools, you can use the tools on your personal desktop computer. It's just that you will have to choose a very small data set to work on to get those AutoML tools to work in any realistic time frame.
Okay.
But if you're looking to get your feet wet, then absolutely get the tools on your personal computer, play around with it. As long as the data set is small, you'll get reasonable results.
Okay. Thank you so much, by the way.
Hey, you're welcome.
Okay, thank you. Thank you very much, Patrick Bangert. That was an excellent talk. I'm sure people will be reaching out to you. We shared your information on our website. I hope that's all right.
Yeah,
so
absolutely.
they will be reaching out to you if they have any other questions, and thank you.
Yeah, please feel free to reach out. I'm on LinkedIn and the usual channels, so look forward to hearing from you. Thank you, Amy.
Thank you.